Alright, so welcome back. In the last video we talked about osmosis and the osmotic pressure, and we did a problem dealing with it. But that was for non-electrolyte solutions. Okay? Electrolyte solutions is kind of different. Let's look at, well, you know what an electrolyte and a non-electrolyte is. I sure hope so. KCl is an electrolyte. Oh, that was a text. And benzene is a non-electrolyte. Electrolytes usually dissolve into ions, non-electrolytes do not. Alright, so we have KCl and C6H6, alright? This molecule works great for this equation. If this was able to dissolve in water, that is. Or whatever it was, well, probably something else would dissolve into it, but for our sake, we're just using this as an example. Okay? So, non-volatile, it works perfectly for this. But why doesn't it work for this? Well, let's think about it. If it dissolves, it's not in KCl form anymore. It forms K ions and Cl ions, right? So it doubled the amount of ions from just one of these. So that's where a new factor comes in. The Hassall factor, where we just add in an I. That's all it is. It's basically the number of ions being dissolved from one molecule, blah, 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 blah. KCl, I would be 2. And this actually equation will work for all of them. The reason why we don't use I for this is because for this case, how many ions does this, or molecules does this form from one molecule? This just one. I mean, it doesn't dissolve or dissociate into ions. So I would be 1. And because it's 1, we can just, and all of these are being multiplied together, we can just ignore it and say just MRT. That's basically all it is. This is 2, so it actually doubles the osmotic pressure. If it was something like, oh, I don't know, NH4, NH4 2SO4, it would dissolve into 3. Okay, so like NH4, oh gosh. SO4. There's 2 ions of NH4 and there's 1 of SO4, so I would end up being 3. Okay? So let's do some practice problems dealing with that. Alright, so what is the osmotic pressure of 680 milliliters of solution of 21.2 grams aqueous calcium nitrate when the temperature is 366 kelvins? Alright, so we know, so we're looking for the osmotic pressure. So this is what we're looking for. We know the molarity. Well, we don't know the molarity. We know, obviously this is a constant, so why even bother? This is the temperature over here. So how do we figure out molarity? Well, I wrote it out over here. Molarity is equal to moles over volume, right? Now, obviously there's a thing missing here. CaNO3 2. What do you think that is? If you said an electrolyte, that's correct. So, we'll have to add an I there. Hassall factor. Okay, and we know what, and from looking at this, it seems like I is equal to 1, and then 2 for every NO3, it would equal 3. Alright, so we know what that is. Now for molarity over here. It's moles over volume, right? Now, we know the volume. And we need to change this to milliliters, okay? So we know the volume, so change this to, not milliliters, liters. So 0.68 liters, right? But we need to know what the number of moles are. Well, we have grams, we don't have moles. Exactly. Moles, or I should say, now we're going to do some conversions here. 21.2 grams of CaNO3 2, and then Okay, so let's figure out what the molecular mass of this is. There is 2 nitrogens, so 14 times 2, plus 6 oxygens, 16 times 6, plus 40.08, I don't know, because that's what calcium is. So 164.08. Okay? So that's what that is. Now, we just need to figure out, oh, I don't know, the next part to this. Oh yeah, gotta figure out how many moles it is. 1 mole. So that all equals to grams. Blah, blah, blah. That cancels. So we get units as moles left. So 21.2 divided by 164.08.129 moles. 129 moles. Okay. So divided by the volume, 68, we get 0.19 for the molarity. Alright, now we just plug and chug. We get that the osmotic pressure is equal to, and we have all these numbers now, so we can just literally just plug it in and multiply all of them together. Remember, the answer we get is in ATM. Okay, so that's molarity. Gas constant is 0.0821. Temperature is at 366 K. And the Hasselhoff factor is 3. So we just multiply all of them together. Times 0.0821 times 366 times 3. We get 17.1 torr. I mean, not torr. Torr in the brain. ATM. Atmospheres. It's pretty large standard, but that's pretty much what the answer is. Okay, so let's try a more difficult one. Let's try out. Sorry about that. Okay, so let's move on to another problem. Now, here is where things get interesting, I suppose. Oh, shoot, no. Okay. I just can't believe that happened. Okay. So, it's basically saying the osmotic pressure of that concentration of HCl is found to be 4.56 atm at this temperature. What is the measured I factor for this solution? So we don't know what I is. But from looking at this, what can we expect I to be? We can expect I to equal 2, right? But from what it looks like, do you think it's going to be a perfectly good round number? Well, we can always check, shall we? So we know that pi equals m RT, right? Times the Hasselhoff factor for electrolyte solutions. Technically the I is in every solution, but yeah. So now we divide both sides and solve for I. So pi over MRT is equal to I. Now we just basically plug and chug. Have the concentration here. We could just convert the temperature here, so we know that K is equal to degrees Celsius plus 273.15 K. I mean, not K. Yeah, plus 203. So basically, we take this and added this much to it. So 54.4 plus 273.15. So we have 327.55. Okay. Alright, so concentration is 0.09 0.28, and remember the answer needs to be in 3 sigmas because everything is in 3 sig figs. This is what we're predicting. Alright, so osmotic pressure is 4.56. If we check units, the units would all be right, but I is unitless. Okay, so R, which is 0.0821, and then the temperature, which is 327.55. Alright, so now we just plug and chug. 4.56 divided by 0.0928 divided by 0.0821 divided by 327.55. So this is what we get here. This answer right here, 1.83. So not much work involved, right? 1.83. So we ended up with I equaling 1.83. Okay. Now, do you think that this is weird? That we ended up with I equaling a decimal number? Now, it's pretty darn close to what we predicted would be 2. Alright, so we can see why. There could be errors with all this stuff, but whatever the cost, we figured it out. We're done here. See you later.